we talked about computational smackdown, and there was this Achilles heel, right, that was there for the spectral methods, which is the boundary condition. I want to talk more about that because the boundary condition ultimately was the thing that limited you from getting your sweet ride in a Lamborghini, right? And so the question is, can you, in fact, modify things and still make use of those spectral routines? Accuracy properties and speed make you think pretty hard about how can I make this square peg fit in a round hole. Ultimately, that's what you kind of do. Like, okay, my guy I drew up on the board, he could totally do it because he's strong. So we're going to try to do that, okay? Everybody play with those round pegs when they were a kid? No? The little thing with the little diamonds and squares and stars, and you put them in that little ball that was blue and red, and you pull it apart and dump them out. Yeah, okay. That's kind of what we're going to do today. So you could take a saw, and that's what we're going to do today. We're going to take that toy, and we're going to saw some stuff out to make the round one fit in the square hole. Okay? That's the concept. So, all right. So let's start off and think about it. So, for instance, I'm going to give you some different methods. I'm going to evaluate them. Method 1. Call this periodic extension. I like my FFT so much. My problem isn't periodic. I'm going to make it periodic. So for instance, I have some function. Let's call it f of x. It's on some domain, -1 to 1. And, you know, let's take a simple function. F of x equals x, for instance. Simple line. That's clearly not periodic. I'm going to make it periodic. So what the FFT can say is, you know, by the way, Fourier said, I can take any function and represent it in cosines and sines. He didn't say, I can take any periodic function. He said, give me a function, I'll make it. Well, how do you do that? What he does a periodic extension of that function. So it's not really that function I'm going to represent. It's this thing, periodic. Today I'm going to blow your mind. Colors. I know. I got the orange tie, green, because like I said earlier, it's the only bright thing you're going to see today. That's like the sun. Think of that, the sun shining today. Okay? So I will not blame you if you put on sunglasses for class today. I'm just going to periodically extend this thing. So here's the function I want in this interval. But really, when I say I'm going to represent this in cosines and sines, I can do that. It's just that what I've really done is made this periodic extension. Okay, so what's the problem with that? No problem, sir. Sir, I have no problems. In fact, if you take cosines and sines, and you take an infinite sum of cosines and sines, it will converge exactly to this. Fourier even says, so what will happen is if you take enough cosines and sines, it will converge exactly to this function, where at the jump, it will converge to the value in between. But otherwise, be exactly a representation of that line. That's if you take an infinite sum. Now, we are not interested in an infinite sum. That's something you play around with in math class and homework, right? We're computing. We don't do infinity. We're going to take n, where n may be large. But that's it. But you know what we're trying to do is take n, where n is as small as I can possibly get and get away with what I'm doing, right? This is our computational issue. We're all about actually doing it versus hypothesizing, can it be done? All right, so what happens when you take a function like this? Well, what happens is you get what's called Gibbs phenomena. Whenever you have a discontinuity, and you're trying to represent a discontinuity with cosines and sines, at the jump, you get this Gibbs phenomena, which is I could represent this, and it does pretty well here, and then right, you get these oscillations at the jumps. And you come here, it does a really nice job, and something like that. So in some sense, you say, well, it does pretty well in the middle, but yeah, right here at the edges, you get the Gibbs phenomena. You can make these Gibbs phenomena smaller and smaller and smaller by taking more and more and more Fourier modes. Okay? But that, again, it can be problematic because if you just keep adding Fourier modes, it's just costing you more. Right? If you want to know the consequence of taking more Fourier modes, take your homework 4 or your homework 5, and you were working with what, 128 by 128 or something like this running these things? You want to know the consequences of taking n up? Why don't you put 1024 in there and see what happens to your code? See how much longer you wait. See how much more computational time it's going to take. Put a thermometer on your computer and see what happens as your code just starts heating it up. You can even sit on it. It's a nice bun warmer. Drive with it. You know, I've heated seats in my car. It's pretty sweet. So you can alternatively just take your laptop, run some of the code with 1024, and sit on your laptop. And if it's running 1024, it will totally heat up. Okay? You know, that one I wouldn't take too seriously. That advice there, maybe you just temper it a little bit, okay? It's the same one as saying if your laptop's heavy, just delete some of the files. Make it lighter. Okay? All right. Okay, so this has some problems. Because actually, this is going to kill you. These Gibbs phenomena is not going to do a good job with you. But that is a method. And you have to, you know, the jumps, the oscillations at the edges depend upon how big the jump is. Okay? And by the way, I give some example of that in the code here. Let me try to see if we can zoom in here on this top camera. Are we ready here? Can we do this camera on top?
We can't do that right now.
Oh, is that thing dead now?
Yeah.
Okay, you guys can look. There it is. Okay, all right. You just have to trust my drawing that my drawing's at least in the ballpark. Okay. So that is method 1. We might want to rule it out if we want high precision. Okay? But you see what we're willing to do this simply because we want the accuracy and the speed of FFT. Remember, if you're going to do a comparison between finite difference and the FFT, what you're trying to compare is order n squared to n log n. So, right? So if you have to take double the number of points, big deal. 2n is still a lot less than n squared. 4n, 10n. Remember, n is going to be like 128, right? So even if you have to take 10 times the number of points, you still win by doing Fourier. Yeah?
So if your problem, you're interested in, I don't know, minus 10 to 10, then in this case you just take minus 20 to 20 if you can define the function and then call it periodic, and the Gibbs phenomenon will be out periodic.
Well, so what you do, so essentially when I draw this function, the way I think of it, that's what FFT is thinking about it. But really, you still define on the interval -1 to 1. And you're just going to work on that interval right there. And because you've enforced periodicity, you'll still see this on the edges. The Gibbs phenomenon.
Context, it turns out the only area you're interested in is the central portion of that.
Here?
Yeah, where there's no Gibbs phenomenon.
Yeah.
Does that come up?
Well,
I guess.
so for instance, suppose you're solving this thing and maybe the solution is actually small at the edges. This is how we argue. In fact, this always happens when you use FFT, right? Most, our homework 4 and 5, periodicity really wasn't what the correct boundary conditions were. What we assumed is that out here, the solution is so small that, so, if it's 10 to the -6, then who cares if you have a little bit of oscillation? Big deal. Okay? Because we're really interested in all the dynamics in the middle here. Okay, so, and in fact, if you're looking at functions that are localized, then who cares? You enforcing periodicity doesn't make much of a mistake. Okay? But if you really have if this is critical to your solution, the boundaries, how they're driving the dynamics, then you're kind of in trouble.